All right, it's 11 o'clock. So this is the NASA Earth Data Past, Present, and Future in the Cloud session. We have 5 talks, but we only have 3 speakers because 2 of our team got waylaid due to various things. So I think 3 of these talks are going to be quite polished. 2 of them are going to be awful. So bear with me. Yeah, one of them's mine as well. So here's the first talk. This is more focusing on the past and why NASA Earth Data went to the cloud. So, one takeaway from this. The reason I give this talk, and I give it multiple times, and I will continue to do it until nobody tells me that NASA Earth Data went to the cloud to save money. That's one of the reasons, but it's not the primary reason. Primary reason that NASA Earth Data went to the cloud is to allow users easy access, all users, to an environment that allows leverage of compute capabilities that are necessary for the explosion of data you are seeing and the explosion of the complexity of that data for today and the foreseeable future. Right now we achieve that by using Amazon Web Services. In the future, we aspire to be multi-cloud because, as my boss Ted keeps telling me, we need to make sure everything's competitive. So moving to a multi-cloud solution provides an answer to that question. So this is the wrong slides. That's a great start. So I'm going to have to... there was a lovely picture here of Helm's Deep from Lord of the Rings, the Fellowship of the Rings, and it said, "Welcome to our data fortress." Let me tell you a second about a data fortress, which is now out here verbatim. So if you are lucky enough to be aligned with an agency or a business concern or a university, then you have at your disposal the ability to download loads of data, put it in your own archive, and fire up high-performance computing capabilities right next to that data. Not everybody has that luxury. So the idea of us migrating to the cloud is to provide that for anybody who has access to Amazon Web Services or Azure or Google Cloud in the future. Admittedly, it's going to cost you some money, but it's probably going to cost you the same ballpark of money that it would be to buy your own local storage and local compute. So the Earth Data Cloud is our data fortress, and everybody's welcome. But as I said, you're going to have to pay for your compute. So if you look at this website in the bottom right corner, this is the original cloud evolution vision for ESDIS and Earth Data. And these were the reasons that we went to the cloud. And they are in a somewhat ordered fashion. Easy access to data, rapid deployment, scalability, flexibility, etc. So I'm going to divide this into two parts. What of those reasons are good for ESDIS and what of them are good for the user? And some of them are good for both. So one of those is scalability. We refer to that as the size and use of the archive can expand easily and rapidly as needed. So this is a projection of the size of NASA Earth Data's archive plotted out to 2030, and you can see it nearly gets to 600 petabytes. We're at about, I think, 172 petabytes right now. With the introduction of SWAP, that ramped up significantly, and with the introduction of NISA, it's going to get even bigger. This is the hockey stick graph that you may have heard of. So that bubble points to where we are right now. I put the "Don't Panic" in large pink friendly letters. Anybody who gets that joke, well done. Anybody who doesn't, read Hitchhiker's Guide to the Galaxy. So as you can see, we're going to have to scale up in terms of our archive needs, and the cloud is a suitable environment for doing that. We also need flexibility as we get new missions. We need to best use the options that are available to us to facilitate those missions. Here we have 3 examples of enterprise offerings that NASA Earth Data provides and the technologies they use to enable that functionality. And you can see there's a wide variety here, and all of those aspects are accommodated for in the cloud. Container services like AWS ECS, managed database systems, on-demand compute like Lambda. We get out of the box with something like AWS rather than having to either build it ourselves or assemble it ourselves on premises. We can achieve reduced redundancy by sharing services across our cloud footprint. You can see the top box of governance. All of the accounts we have in AWS, whether they be for a DAC and their ingest and archive capabilities, or for a particular mission-oriented service like Appears or Hype, or a shared service like CMR or EDL, leverages things like cost control, account management, continuous integration and continuous development through these shared services, and that's really easy to do on the cloud. But what's in it for the user? Again, the most important thing that I mentioned earlier was easy access to data. So before we had this entire infrastructure in place, if, for example, a scientist using INSAR wanted to produce some science, it was quite a cumbersome process. And it's a specific example that I saw demonstrated in 2021. They needed 4 terabytes of data to download, and it took 107 days of processing to get it onto their local compute and process. That's a significant amount of time. Now, using one of those services I mentioned, Hype, which is completely on the cloud, adjacent to the data that they need to provide that science processing, they managed to observe an event in April of 2022 and publish in October of 2022. And I asked that group how long it would have taken for them to do it the old way. And they said they'd still be downloading data in October of 2022 in order to achieve that. So this is a good example of fast science in action due to the cloud. Another good benefit for the users is they can rapidly deploy managed services. Each of these cloud providers, and I'm going to focus on AWS here, provides value-added services that they manage. So for scaling and orchestration, they provide managed services, analysis pipelines, databases, machine learning, reproduction of your science through Jupyter Notebooks. They have services that provide those capabilities that you can leverage immediately adjacent to the data. And it's also cost effective in a lot of scenarios. You get to rent large amounts of compute for short periods of time, and then you don't pay anymore. Whereas if you'd have bought your hardware and your compute and your storage for on-premises, you basically got that until you throw it away. There's also an economy of scale aspect to this. While it's very expensive for you or I as an individual to buy an Oracle license, AWS can buy hundreds of them and get a savings there, and they do pass some of that savings on to you when you're buying Oracle relational databases from them as a managed service. And also, with an Oracle license, you're bound to a pretty large granularity of time where you can spin these up and down in minutes and only pay for those minutes. And finally, one thing that's not mentioned in that manifesto from ESDIS back in the day, and something that was brought to my attention recently, is that underserved communities can also benefit from this paradigm. If you're doing a large download of data, then you're dependent on your ISP. And in certain areas, your ISP is a big risk to you producing your science. It's not reliable, it often goes down. So if you're doing all your compute in the cloud in US West 2, you don't suffer from that same problem. Also, each of these providers has outreach programs to underserved communities to give them compute credits. So they can, in theory, do this for free under certain circumstances. But the biggest deal I find with looking at cloud for your solutions is this paradigm shift from owning your resources to renting them and then giving them back. Now, the advantage of that is you only pay for what you use, but the disadvantage is you're paying and you're paying again. And the analogy I like to use is consuming music analogy, whereas in the old days you were buying vinyl or CD or cassette, and you had that forever. But now you're streaming your music, and if your streaming subscription expires, you don't get that music anymore. But the wealth and depth of music that you can have at your fingertips is so much greater. I was a little skeptical, being a bit of a muso, I was a little skeptical of doing this myself, but then when I realized I could go through Kanye West's entire back catalog in an afternoon without paying much money to see if he really is a genius, I could do that. I could go through like the top 50 albums of krautrock without having to go buy a bunch of music that I might not listen to again. And that's what I've done, and it's been really useful. Now, this is where I had a really cool graphic that was on my other thing. So, the greatest album of all time is Unknown Pleasures by Joy Division. I have this on vinyl, I have this on cassette, I have this on CD, I have this on MP3, I have it on streaming, all right? So that is my level 0 data in Doug's world, all right? I have it on all these different formats. The other greatest album of all time is Marvin Gaye's What's Going On. I was introduced to that a little later, so I don't have it on vinyl and tape, but I have it on CD, I have it on MP3. That is level 0 data as well. Both of those things need to be on a gold record on Voyager, right? By the way, Joy Division, not for everybody. A little bit depressing, so you might not want to seek that out, but Marvin Gaye's What's Going On, everybody should listen to that. But Rachel Patton's Lone Ranger. Terrible song, quite catchy. My daughter loves it. I kind of like it. I don't want to own that. But I will listen to it in the car on occasion. That's what I would refer to as level 6 data, I think. May the force be with you. Thank you. Any questions? No, I finished early so I could get some questions. Come on. There he is. Hey, there you go. Come up and take a mic.
Questions, please speak in the mic, please, so online folks can hear.
Hey Doug, this is Kip McManus from SCF. I'm wondering if you could say anything about, you outlined how it's great that we have these ephemeral computing resources, we know how much they're going to cost. What about when we're doing experimental research and we don't really know, is my algorithm optimized for this yet? Maybe I have to run it a few times to see if it's optimized. Do you see any risk in that? Is there anything you can say about that?
So your risk is the possibility that an unoptimized algorithm is going to run up your bills, right? So I think that's a fair risk, but I think you're mitigating a lot of other risks using that environment in terms of development costs and things like that will outweigh that risk. So for example, the ability to run that algorithm in a variety of environments using a variety of technologies, you can mix and match quickly and rapidly. I would hope that would outweigh the risk of an unoptimized algorithm blowing your budget. But that is that is the main risk associated with it. The tap is always running, the bill is always increasing. So always remember to switch everything off when you're done.
We have another question, but I would like to ask the speakers to please repeat the question at the podium because the online folks can't hear through this mic.
Even with the mic? Okay. So the question was... All right.
Maybe starting with the next question.
Okay. My boss is about to ask a question. Please hold.
It's more of a comment, and I just want to point out that when the supercomputing environment first came out, basically the scientists had these same type of questions. It was largely experimental, but over time they figured it out. And we see the same thing happening with the cloud. With the early adopters, there's a lot of things that kind of worked out. Of course, there's this kind of scary in the beginning. But just like science did with the supercomputing environment, we expect the same to happen as they become more mature in the cloud computing environment. Right? So, and then we have a lot of early adopters leading that way. You will come here, open stage, give a talk, and things like that. So we're making a lot of progress in that area of understanding cost and definitely taking those concerns into consideration.
I have an online question here from Carl Benedict. He asks, how do costs for transfer out of the cloud figure into the cost allocation calculations?
So that's basically egress costs. I got to repeat that question as well?
No.
Yes, please.
All right,
If
so-
you're online.
So we talked about, you've got two components towards the cost of data storage. One is the actual storage of that data, and the other is when anybody asks for it and they transfer it out of that system, there's an egress cost associated with that. So the cost of storing that data is a pretty well-known quantity in general. You know how much data you have, but you don't know how many times people are going to try and egress of that data and how much of it they're going to egress. So that is a reasonable risk, something that ESDIS has put a lot of thought and effort into. We have a lot of cost controls associated with data regress, but we're beginning to investigate whether the cost of those, the risk associated with the cost of those egress controls matches the risk of that egress. So we're still working that out, but it is a genuine concern of ours and has been for a long time. But we're starting to wonder whether our initial risk evaluation was way higher than it actually was, or it's panned out to be.
I got a lot of questions from users. They want Google Earth Engine on AWS. Do you have any plan to do that?
I don't, I'm not an expert on Google Earth Engine. So the question was, can we run Google Earth Engine on AWS? I don't know the answer to that question. I would suspect not, because it's a Google product and AWS, so. All right, maybe you should answer this question then, Nick.
Like Doug said, I would estimate that no, that's not feasible because it will be competing with, Google has their own version of a cloud and Amazon has their own version of Google Earth Engine. It's not as fully fledged necessarily as Google Earth Engine, but it seems like in that space they would be competing with each other. So I would surmise not, but I don't know for sure as well.
All right, I think we're going to move on to the next. So, Nick, you can come back up because it's. We need to start Zoom off again, right?
So which presentation do you want to share?
It's one of them.
Okay, great, here, wait, first, hang on one second, we have to go to full screen. You're good, you're good.
Order of operations.
How do I move forward, arrow keys, just click. Oh,
Sorry, hang on.
It's still showing the presentation
Yeah, hang on one second.
in the screen.
Yep,
We're good.
good now? You can use this if you would
Excellent.
like,
I don't
or
have-
the
well,
arrows.
people won't
But
be able to see
You should
me.
stand near the microphone.
got it, okay. Good morning, everyone. I think I know about a fifth of you in this room. So for the other 4/5 that I don't know, I am not Ben Williams. I am a bald Dollar Tree version of Ben Williams. Ben was unfortunately unable to make it today due to some unforeseen circumstances. And so I am stepping in for his presentation today. But I know it's going to go really well because I forgot to wish my wife, my 9-month pregnant wife, happy anniversary this morning, so my day can't get worse. I noticed after my mother, my father, my father-in-law, and my mother-in-law all messaged us, and I went, oh. So let's see how this goes. So we're going to talk about doing cloud cost management at scale, something that NASA is very well versed in because we have one of the largest clouds that I've ever seen, and I've worked with a lot of federal agencies. Our understanding of what big data is kind of outscopes what a lot of other agencies would necessarily see, given we are working in the petabyte scale. So in order to make sure that we're not overspending and working with them on our budgets, our cloud cost management is something that we focus on quite a lot. So we're going to talk about motivation and then how we work through estimation, monitoring, optimization, and protection. So I believe also Ben is online. So if I screw something up, I'm really sorry. So for motivation, so we have a very, very large cloud ecosystem just within our own development and as well as what our user base uses. We have over 350 developer accounts. We have over 400 endpoints. We have over 100 petabytes of S3 storage. For reference, Amazon Web Services lets you charge at the gigabyte level. So we're talking millions of gigabytes. The dollars add up. And so in order to make sure that we're not overspending, we're being diligent with the way that we spend on cloud costs, we've had to create a way in order to maximize our use of dollars and technology to get the best bang for our buck, so to speak. So there are lots of things that also can derail this train, so to speak. Cost threats, things like infinite loops, during testing, which is something that is very rare but has happened. Demands due to natural disasters, things like the most recent hurricane that came out, fires, a lot of wildfires tends to be something that brings people into our system because products like firms are a great way to look at the different places that fires are taking place. And then things that could potentially be malicious, like a denial of service attack, are all things that we have to keep in management. So our approach for managing those cloud costs. 4 pillars here that Ben's laid out. We have estimation. So the processes and tooling to generate increasingly accurate estimates of future costs. The cornerstone of where we start is trying to estimate as best as we can what we're going to be spending in the future. Next is monitoring, observability and analytics over historical and near real-time cloud cost actuals, making sure that as time goes along that we're able to collect and understand how our data is being used. Is it matching what our estimation is? And then do we need to make any adjustments moving forward? Protection, analytics, and automation to avoid cloud cost overruns. Doug touched on this a little bit. A lot of things that we will do for protection are things like the dev accounts in case they have a piece of malformed code and they end up just spending more than we intended. Things like egress that are very volatile in our system. We can estimate how much is going to egress out of our system, but we don't necessarily know if a user is going to come by and download petabytes of data at a time, which has now happened on more times than I can count on one hand. And finally, optimization, methods for identifying cost reduction opportunities and mitigate cloud cost waste. This is something that I'll touch a little later in my own talk, but we've got all these technologies out there. We're no longer a new system in the cloud. So what tweaks can we make to ensure that we're using our money as efficiently as possible? So first, cost intelligence and event management. So if you think about the way that you're spending in a cloud, you can just treat it like any other data source. If you combine the information about how you're spending in the cloud with things like distribution, egress, storage, you can get a bigger picture and make better estimations from that information. So we elevate the community practice of cloud cost optimization to the same level of tooling and scrutiny as cybersecurity. For example, the security information and event management system. So this is a graph that I actually don't know where it came from. I'm sorry, Ben. But it kind of goes over the ways that we use and collect all of the information. And then through a system of data analytics that our organization has created, we can get a lot of information out of that. Things like alerts for when we're reaching egress thresholds, dashboards where our tenants can look through the information and determine what is being accessed in real time, what are people most interested in, is there any way that we are using things inefficiently, as well as things like forecasting for improving our metrics and our estimation moving forward. And then as this was written by Ben, so making recommendations to the ESDIS program as far as what changes they think that would be best suited for our environment. So for estimation, one of the tools that we have is called the Cloud Resources tool. We call it CREST in our program. And CREST is a system that allows our tenants to enter into a litany of information, and then we will provide them an estimate for how much their cloud costs will be. And so in the system that was before CREST, it was a lot of spreadsheets, it was a lot of emails, it was a lot of information going back and forth. It wasn't well tracked. And now the CREST tool is an application that is available online that our tenants can go in, and during our budget cycles, they can enter in information about their usage, and then we can provide them an amount and how much they're going to spend that year, and then we turn that into what we actually spend. So how that starts is our tenants start with what is the AWS pricing calculator. This is available to anyone that wants to work in the cloud. It gives you a rough estimate of what you'll probably be spending given the information you put into the program. It's not perfect because, again, you can't estimate things like egress because you might have an actor that comes and downloads a lot of data, but it's a really good starting point. From there, it goes through an estimate process, and it goes through several workflows of approval. So where individuals are looking over to make sure that there aren't typos in the system, there are things that are accounted for that might have been forgotten, et cetera. And then, as part of the third part, is where we start to do the automated cost protections. Things like making sure we don't overrun on our spending, throttle limits, egress limits, so that we don't necessarily turn things off, but we know before we overspend our budget that we're getting close to that. And then finally, as part of our metrics, we calculate or we collect all of this information and we turn it into cost analytics, where we can look through how our spending has gone across the future, and then we can optimize from there. We can take that information and make better decisions. That means that we spend less money or spend it more efficiently. So this is a graph of our budgets versus our actuals. And this is something that was enabled by CREST from the information coming in and then going through our cloud metrics systems. So you'll notice on the graph on the left that the green lines and the orange lines don't necessarily match up, because although our estimates are trying to be as efficient and optimized as possible, there are things that change. And so we have some tenants that are excellent at estimating their use cases, and some that have so much information going in and out or so many complex processes that it's not as easy for them. And so those are why we use some different tools for monitoring things like egress, putting on rate protections. The green lines and the red lines over here are different types of warnings. So the green line would be a warning that you're approaching your egress threshold. Red is, it's time to put more money in the account before you go over. Again, this is something that Doug had talked about, because this is a very, it's a useful tool, but it requires a lot of time and manpower to do. And we don't necessarily want to turn off egress. We want to make sure that users can access our data. So turning it off is not something that we're necessarily interested in. And so is the time and effort spent running these cost controls manually worth what we're getting out on the other end? So for protection, doing automated cost overrun protections, we have things like putting limits on how many or how accounts spend their money. We can do a freeze spend, which means that you can't spawn new resources in your own account. Circuit breaker will suspend the compute or network resources if somebody is spending more money in an allotted amount of time than we've necessarily designated. And then we also have egress distribution limits, where we will throttle, slow down the distribution of data. And if we get all the way to the top of that red line on the previous graph, we'll go ahead and cut off the data being distributed. Both with push notifications in advance of automated actions, so that these emails and information are going to the owners of these accounts to make sure that they're on top of them before it becomes a problem. So optimization. We have to understand where we're spending our money in order to understand where we should be spending our optimization time. This is, I think the term is low-hanging fruit, where you want to spend, you want to find the areas where you can optimize the most by spending the least amount of time. From this breakdown of the graph, most of our spending goes to Amazon S3 storage. After that is EC2, RDS for databases, and then it gets smaller and smaller from there. So the areas of focus are obviously going to be things like S3 storage and EC2. So for S3 storage, we have access to things like storage class tiering, where you can move the data in between storage tiers, which can provide you savings, but depending on how the data is being accessed. For EC2 instances, making sure that they're the right size for your application, limits spending, and making sure that if it's not a production system, you can turn it off when it's after hours or over the weekend, so it's not spending while no one's developing on it. For RDS, again, the same thing with using reserved instances, and right sizing can help eliminate costs that aren't necessary. And for CloudFront, they have discount programs for research institutions that can allow for some savings as well. So for that optimization for focusing on S3 storage classes, this is something that we spent a considerable amount of time investigating. At what point should we be moving data between S3 storage tiers in order to optimize our spending as much as possible? If you're not aware, there are maybe a dozen different S3 storage tiers, but the ones that are most primarily used in our organization are going to be S3 standard, S3 infrequent access, and then the instant access glacier tiers. Each of those has pros and cons. The S3 standard tier will be the cheapest for egress, but the storage is more expensive. Whereas for infrequent access, storage is cheaper, but egress is more expensive. So if you place something that's accessed a lot in infrequent access, it might be more expensive than placing it in standard because you have to balance the cost of storage and egress at the same time. This is something that we are constantly examining, trying to calculate where data should be to make sure our costs are as low as possible. Recently, we were given access to intelligent tiering, and that is a system that allows the data to move freely between the tiers that Amazon will track for you. Which is something that we're currently investigating. There are a couple of our tenants that have started using this, but it's something that we just got access to about 3 weeks ago. We're very interested in where that could go. And then there are tools that Amazon provides as well that help with analyzing this data. Storage Lens and Storage Class Analyzer give you insights into how your data is being used, where data is being stored in different storage tiers, and recommendations on where you could move that data. There are some free tiers for both of those, but the vast majority of the data that comes out of them is paid. And that's apparently the end, so. Do you have any questions? Oh, no. Just please remember, this was not my presentation, so.
Please repeat the questions.
I can repeat the questions, thank you.
This should hopefully be really simple. Did you actually use the AWS as stair step to write your circuit breaker or actually the actual protection limits for the spending, or did you actually use, I guess that's like my question is, did you use AWS's certain stuff to actually implement your circuit breaker and reduce your spending?
So the question is, did we use the AWS systems to implement the cost controls like circuit breaker? And I believe so. Neil, do you know? Sorry.
So as you probably know, AWS doesn't have any actual controls to stop costs, but they do have a bunch of monitoring tools to monitor costs. So we use a lot of the monitoring features in AWS, combined it with custom code and some off-the-shelf software. Kion is one of the tools that we use. And based on what Kion sees from AWS, then we implement our custom code and turn certain things off. It doesn't catch everything necessarily, but we can version that code to make sure that we catch more things.
So for those online, the answer from Neil was that Amazon doesn't have those tools built in, but they do have monitoring tools, which we combine with some custom code that we write for our specific systems in order to throttle or turn that data off.
Ben says yes.
Ben says yes.
This Crest tool, is that something that data centers, like any back, has visibility into, or is that still as this?
The question was the CREST tool, do data centers or DACs have access to that tool? They should. If your funding for your cloud accounts comes through the ESDIS program, then you will be filing what we call CAPS, annual cost allocation plans, and Cosmos cost models for the 5-year PPPE cycle those are something that you will do annually. And actually, I believe the training was yesterday for that, so.
We're doing it right now, yes. We are the tenants, the DACs are tenants in that scheme.
No, my point is this something that we have, like, almost real-time visibility, or is this only a planning
It's only a planning tool.
initiative, right? So we won't be able, as a DAC, for example, my users and, infrastructure folks, can they tell if they've hit that critical limit today or not?
So there's a little bit of complexity. So the question was, can users go in and see if they're hitting those thresholds that they set in or the limits they created in Crest today? There's a little bit of complexity in that because with the pricing calculator and with the Crest tool, everything's done at rack rates. NASA has a discounted program through AWS that gives us not rack rates that we're not really at liberty to discuss what those discounts are. So if you go into something like Kion and look at spending, or you go into your bucket or your account in AWS, the spending that you will see will not be rack rates. It'll be current spending. And so matching those up can be a little bit difficult.
I'd like to piggyback off that and also mention that, yes, so the DAC managers and management of the DACs, they'll have access to the tools that he discussed. And it's not maybe like on an instant real-time turnaround, but definitely within a 24-hour period turnaround. If people are hitting, like if they're hitting their upper egress limits, you will hear immediately, the DACs will hear directly that they, NGAP and other team receive notification, and then they contact you, the DACs directly, and then you can go through an iterative process with your DAC engineer to make sure that you are planning appropriately and adjusting as you need. Does that help a little bit? Yeah, okay, cool, thanks.
And AWS allows you to set alerts depending on what percentage you're hitting for your budget.
I wanted to add quickly that every DAC, every developer every tenant in the cloud that can actually monitor their budget, the burn down of their budget, makes this whole thing work. Because it can't be centrally managed, otherwise we would have very bad cost controls, in my opinion. So if you can't see something, if you're not getting an alert when something changes that's critical, we want to turn it on and make sure that you have instant access to it at any time. So if you see something that's a better thing to do, we want to do it.
I think we're out of time, Sandra. We should probably keep moving, so.
Okay, thank you so much.
Great job, Vinny.
All right, so we're moving into that phase about away from the past into the present, about what we're able to achieve through leveraging the cloud, which was a lot more, which we either couldn't do or was a lot more difficult when we were on premises. So this is not me. Jonathan was unable to be with us today. His problem was CrowdStrike. Fun fact, I was in the line for screening at Reagan on Sunday, trying to get out here, and there was a woman with a CrowdStrike t-shirt on, which I thought was a bold look, given the circumstances. But anyway, so this is Jonathan's talk, but I'm going to give it, so let's go. So this is NASA Earthdata's global metrics portfolio. For business intelligence, we use QuickSight and Oracle Apex. For near real-time analytics, we use Kibana and Elasticsearch. But for operational insights, we use CloudWatch, which is AWS managed service for monitoring your system or systems. And that's what the focus of this talk is going to be. So to set up CloudWatch, it's relatively simple. You grant access to CloudWatch for your compute, whether that be EC2, a container, or a Lambda. You install for EC2, you install a CloudWatch agent onto that compute, and then you run a setup, and the agent will start forwarding logs and metrics to the CloudWatch system. So in terms of the progression of insights we get from that CloudWatch systems, at the lowest level, we have logs, which we can expect. We can make measurements from those logs. We can do analytics based on those measurements. We can put alerts in based on that analysis. If a threshold is broken, we can send alerts to the people who can do something about that, or the systems that can do something about that. And we can also make predictions about the future state of our systems through the analytics as well. So at the lowest level logs, you can go into CloudWatch and actually look at the logs themselves, kind of what I used to do in the good stroke bad old days of being an operations lead on Eostis. But we can also query those logs now using natural language. We can filter on certain fields. We can provide and filter your log entries down to a specific set that you might be interested in that might revolve around a specific event. As you can see, something happened at 4 a.m. that this user was interested in, and they've narrowed down their search to that particular time and probably some particular types of events associated with what they're interested in. We can also use those logs by indexing fields within those logs to make measurements, possibly like looking at the HTTP access log and finding out, what the distribution of 200 or 400 codes was over time, which is what this particular example is doing. And we can develop insights from that. There are several out-of-the-box metrics that you can measure for different types of compute. In the case of EC2, it will automatically track memory usage, CPU, disk used, input and output for disk and network, etc. So you get those for free. But you can also implement your own custom metrics as well. Once you've got those, you can use something like Kibana or CloudWatch's native tools to visualize that information in a variety of ways. We've got the standard time chart at the top. We've got a donut here to divide HTTP responses by type, and histograms, line graphs, etc. All of which can be used to try and figure out exactly what's going on with your system and other systems within your account and how those systems might be interacting with each other. The next stage of that trace was alerting. Now that we've got our metrics and we're able to track them, we can set thresholds to describe when the system is in a untenable state, when it's using too many resources, or when it's got enough it hasn't got enough resources at its disposal to do its function. We can set up alerts to describe that anomaly and communicate that alert to either other systems using SNS or via SNS to send emails to operators, etc., so they can do something about the anomalous state. Once you get that alert, you want to do something about it, and that can either be some manual intervention, or we can also add automations. You could, for example, have a cluster of EC2 instances that will receive an alert saying that they're starting to run out of resources, and we can automatically add EC2 instances to that cluster to alleviate that pressure on the system, which is what we mean by self-repair. And then finally, we can use CloudWatch's built-in anomaly detection to analyze those logs and look for potential problems that may occur in the future. Thresholds are a very simple example of that. When a certain threshold is tripped, something happens. But a trend in the pattern of behavior can also be analyzed to detect more subtle problems within the system using things like machine learning, etc. And we can also use that built-in anomaly detection to define metrics thresholds. We would say, if the CPU utilization of an EC2 instance goes above 80%, then we should do something about that. But there are more subtle indicators that problems have occurred that we should do something, like a sudden jump in utilization or a specific pattern that matches a known problem that we could ascribe to some mediation is required. Okay, so this is where I get to the point where I'm not so sure about this slide. I got quite far before I started floundering. This is good. We can apply these tactics to various metrics. CPU usage, HTTP response. As you can see from HTTP response, we've got the ability to plan for those right across the board, with the exception of AI and machine learning. That's something we've got to investigate. And that appears to be the end of my slides. Any questions? You, sir.
Yeah, I understand that this isn't your presentation, but what use cases do you use monitoring for, and which use cases do you use monitoring for, and how have you scaled it out?
So, CPU usage is a good example. As we get pressure on the CPUs in a particular cluster, they all trip over a particular threshold. They're going to start to fall over if the usage increases, so we just horizontally scale out, add another EC2 instance, and then in a lot of scenarios that CPU usage will go down, and we avoid the risk of degradation of performance in the system. Like CMR, for example, currently has a sub-second query response at server for searching across 1.4 billion granules, right? That's pretty impressive. But as more and more queries come in, that service response will degrade because there's more pressure on the system. So we alleviate that by adding or subtracting the number of EC2 instances in that cluster. So we scale up when there's increased usage, and we scale down, and that makes cost-effective sense as well. Okay.
If you wanna this was a question after the last talk, and then this is response if you want.
Okay.
If you wanna share that.
Can we address those at the end? I think we've got some time, because that's going to take a bit. Any other questions on this session? Neil, I gave Neil instructions not to heckle until we got home. What you got, mate?
You did say that. Just a quick comment on the planning for your analytics. When I see that chart, first thing I think of is some lessons learned. If you wanted to turn on, for example, extended logging, that has a cost to it. AWS will charge you for that. And that kind of planning allows you to decide whether or not you actually need those extended logs and metrics before you turn anything on. So you probably have to pay for something in a dev or test environment in order to understand what you will need in a prod environment. And once you have that data, to give some more commentary on the previous question, sometimes you want to have an automatic response to an alert to automatically scale out a cluster, for example. But sometimes you just want to push a code update to make sure that you turn on swap memory, for example. Like the standard EC2 instance doesn't have swap memory. Maybe you have a memory problem. And maybe the memory is not performance related. It's more like there's a lot of idle processes on your instance that need to go into swap, and that would make things fine. So it's a bunch of different responses.
Screen 2 has vanished. I'm trying to set up the next presentation and failing.
You have to share first.
All right.
And then once it's shared, do full screen. And then do share. And then do screen.
And screen 2.
And then if you do more hide floating meeting controls.
It looks good on the screen.
And then click back into the, yep, now she's. and you can-
Jess, everybody.
She is actually
Thanks.
presenting her own presentation.
Yes, I know, and maybe some of you guys are surprised I was here because I wasn't on the website. So, hi everyone. I am going to use you guys as guinea pigs as I practice not speaking so quickly. So those awkward pauses are on purpose. So I'm Jess. And I'm going to be spilling the tea on Earthdata Cloud today. And before I forget, I just want to thank all my colleagues, both at the ORNL DAC and across the greater ESDIS community, because as you can tell in this room, everybody is really supportive and helps answer questions. No one is an expert on on everything. And so we get a lot of support in sharing information from everybody, and it's really great. I just love to see everybody helping answer questions for each other. Again, I am Jess, and I have a fancy title in this Earthdata sphere, so I am called a Scrum Master. And that's also known as a team coach, or an agile cheerleader, or I like to refer to myself as a herder of cats. And according to Scaled Agile, I am a servant leader and coach for an agile team who facilitates team events and processes and supports teams in agile release trains and delivering value. So I know that everybody thinks I'm really, really important now because of that very detailed description. But really what I do is I help our teams, development teams, anybody that is working in this migration to the cloud, do their jobs, get rid of blockers for them, help communicate across different teams and different levels across this whole system. And so I am on the ingest and archive release train for this scaled agile framework safe process, and I represent the ORNL DAC. So you might have noticed my slides are a little bit different from the previous slides because I'm not one of those fancy at NASA people. I'm at ORNL. And so ORNL is the Oak Ridge National Laboratory. We have an interagency agreement with NASA so that we have one of NASA's data archives on site. And so, am I a cloud expert? No. I'm like a capybara in that I have lots of associates from diverse backgrounds who help me give forth the information that is there. So I'm not a cloud expert, but I know some, and I can ask all of those different people what I need to know to then present the information in reports or to through outreach, all those kind of things. I know a lot of you in this room are quite familiar with this whole system, but I just want to make sure no one's getting left behind. We have these things called DACs. They're basically a data archive or a data center. NASA has several of them. It's this distributed system of data. So traditionally what happens is the Earth data that is collected for NASA, so PIs are given money, or principal investigators, professors, people at laboratories are given money from NASA to do data collection for NASA. And part of that requirement is then giving that data back so that NASA can then distribute it for free to the world so that everyone can use this data to do their science. So traditionally what happens is those PIs give their data to NASA and NASA says, all right, we need you to send it to one of these archives. So these archives are domain specific. Because domains are different, there's different data formats with varying standards and metadata. And what these DACs do is focusing on supporting the data producers and the data users. So we help the data producers submit their data, curate their data, write guides for their data. We help users understand the data, read the guides, we make services and tools so that those users in those domains have an easier way to acquire the data. So as I told you, I'm at the Oak Ridge National Laboratory DAC, and we specialize on biogeochemical dynamics, ecological data, and environmental processes. So the types of users that we have are different than the users that you might get at LP DAC. And so we see more like ecologists and environmental sciences, a lot of field people, whereas the LP DAC might have more developers and remote sensing scientists. And so these DACs are here to support those users, but also support the data producers. So how are things changing under this new paradigm of the cloud? So traditionally, these different DACs all maintain their own on-premises servers and their own products and services and tools that fit the needs of their users or their domain. What's happening now is we're taking all that data and we're putting it into the cloud space so that all the Earthdata is all in one place, so to speak, rather than being distributed across these archives. And that, in theory, is going to have a lot of benefits for our users. But how does that affect the DACs, right? What's the shift like for the DACs? What is it looking like? How do we feel about this? Well, first, how do DACs actually go into the cloud? So very, very, very simply put, this is what I've seen. My background is as an ecologist. I am not a computer scientist, and this is what I've seen happen with the DACs. So first, we migrate our on-premises data sets into the cloud. So now they're both, they're in the cloud, right? And you can access them through those cloud tools, but they're also still available on premises as they have been. Next, we're starting to modify the data sets and also work with developers to make cloud-based services that work with those data sets. Next, we'll start enabling cloud-only data sets. So that means you can only access the data through these cloud infrastructures rather than hosting them and accessing them through our on-premises servers. And then we go toward this native, cloud-native publication. So instead of using our tools on premises to ingest and curate the data, we're just going to start ingesting and curating them and publishing them straight to the cloud. So we won't have to migrate our data sets from on-premises into the cloud. ORNL DAC as an example. People are in the cloud. This is what this graph is showing you. People are in the cloud. We have users on the y-axis and we have time on the x-axis. And so ORNL DAC, the ORNL DAC, went into the cloud around late 2020. And so you can see here, yes, we still have most of our users getting our data from our on-premises. However, we are starting to get more and more people accessing the data through the cloud. So now we know we got users in the cloud, we got DAC people in the cloud, but how has the cloud impacted the DAC operations? So the questions that were posed for this session was, what has the cloud allowed us to do that we couldn't do before? And what will the cloud allow us to do that we can't do now? So here's where we spill the tea. So first we have sweet tea. So these are some blurbs that I have collected across the DAC folks and the DAC affiliated folks. And I'll give you guys a second to kind of take this in. So we have sweet tea in that there's some positive comments here. So a lot of it is about data accessibility. Data can be accessed using these common routines that can be shared and streamed in smaller chunks. It provides us more options for accessing data because it can be accessed directly or streamed. Applications can access data from multiple sources and produce products that we want without having to download any data. One person said that the tools and services can easily access data from other federal archives that are in the cloud, so greater collaboration and interoperability. We're moving towards a DAC agnostic search and discoverability. So instead of the users having to go to all these different DACs to get the data, they're getting it in one place that is streamlined and functional. And that makes it so that DACs can have more time to actually serve their users within their domain. And another really great comment is for within the DACs themselves, DACs can more easily access and communicate with each other through this common system. Plus, our SAFE process adds this functionality and consistency. So we're across all the DACs, we're all following along, the same playbook and collaborating with each other a lot more. So some kind of these mixed responses here, which I called Arnold Palmer. So the DACs will be able to focus on users within their science domains instead of using a bunch of their time maintaining their on-prem systems. It's just not yet. We're not there yet. We're expecting to be there at some time. So I can tell you at the ORNL DAC, we have people from other projects, like in computer science and things like that, that help us with the development and the delivery of our data. But pretty soon, we're going to need less of that help because all of this is going to be within the cloud. Another person said, although somewhat painfully, we are discovering things, right? New file structures and formats that allow for cloud optimized performance. So it's, it's causing a little bit more of a headache, but we are learning things and evolving with the technology. Then the cloud scaled processing should be particularly helpful for our data providers when they're reprocessing data sets. So because we're going to have this really streamlined scheme for ingest, it should help our data providers give us the data quickly, which is ultimately going to help our users, right? Because they're not going to have to wait as long for their new data to be delivered. And then another one was about the true power of the cloud hasn't really been realized by the DAC yet, especially AI. So thinking forward, how is AI really going to play into making this system and the different uses that we need out of the cloud better? And so the last ones are a little salty. So maybe you guys have heard about this idea of putting a dash of salt in your tea. Maybe it's supposed to make it taste better. I don't know. But I like these comments. So what's something that the DACs can do now that they couldn't do then? Someone says nothing. It's just different. Not anything we could or couldn't do before. Another person says, I haven't really seen anything that's really beneficial for us or our users, but I suppose that if a user can afford to purchase cloud resources, it's probably going to be really helpful for them to do things quicker. And another comment was that it takes a whole lot of work to get these old data sets that people probably aren't really even accessing that often, to get them into the cloud. The same thing with heterogeneous data sets where you have granules of different types, they're not easily fitting into this cloud structure. So there's a lot of time that's going into this integration when our on-prem systems already work. So what do we want to take away from this? Well, these things that are underlined here are all the different reasons why we have moved to the cloud. So that reduced redundancy, we're seeing that. We're seeing the use of a common infrastructure that makes it easier for these DACs to communicate with one another and for users to access the data. The easy access to the data, so you don't have to download the data. You can use it within the cloud if you want to. We also have cloud processing that will expedite data updates and delivery, just eventually. We have that scalability, so we can change what services and how much data we're delivering depending on our needs. The flexibility, so we can actually serve science communities and ourselves by getting the tools and services that best meet our needs. Hopefully, we're going to be able to better serve our science teams and users once we've actually shifted. And there are a lot of optimizations and potential uses. It's just kind of painful, right? Those growing pains to get there. We see cost of effectiveness for the actual DAX and everything, but it can be a little sketchy for users because it's kind of pay to play with they really want to benefit from all the uses of the AWS environment. And then we have our rapid deployment, so that simplified procurement and expedited science. So again, how can we serve our data producers and our data users by getting the data in and out into the world more quickly? So a little plug for our friends at OpenScapes. Like if you are working within the cloud or you are working within a DAC and you're working towards moving into the cloud, like there is help for you. There's this OpenScapes framework, particularly I'm talking about the one for NASA right here, where OpenScapes is working on helping the NASA DACs with migrating their workflows through a mentor community and sharing resources and sharing training and just essentially making open science and the world of data much more habitable and kinder to everyone. And there's a link to it, and that is the end of my talk. All of the technical questions will go to my colleagues. Thank you.
Questions for Jess?
No need to answer this, Jess. I'm just giving a plug for the OpenScape session, which is in this room at 2 o'clock this afternoon. If you're interested, come there. Thank you.
Yeah. Other questions? We also have a lot of time set aside for questions for all the speakers.
Yes, I did want to say that if there are any DAC folks or DAC affiliated folks, I would love for you guys to spill the tea right here live and on the computer if the virtual world is out there. Let us know.
Yeah, I like that.
I'm back. You're just gonna have to watch me set this up because I don't know what I wasn't paying attention when we did this earlier, so. There we are, that one. I think it's a little nonsense that Jess gave her own presentation and didn't get questions, but Doug and I gave other people's presentations and got questions, so rude.
Share yours,
Yeah.
hit share,
And now,
go back to share.
I'll go back.
First you have to do.
Do a pirouette.
Does it take?
I don't have a PhD.
Well, that explains it.
I also don't have a PhD, so.
Have you met this guy?
Are good now? So in retrospect, I realized that I explained to everyone that I'm not Ben Williams, but I didn't tell you who I actually am. So that was a smart move on my part. So my name is Nick Doty. I'm part of the ESDIS project. I oversee the platform team, which is a lot of the cloud computing and on-premises resources. I'm also a cat herder, but only because I have 4 cats at home. Want to thank Jess. She actually did a great job speaking slowly and slowing down. I have ADHD and I'm really passionate about this, so this is me talking slowly, so we'll see how fast this goes. So we just heard a bunch of great talks about why we went to the cloud, what are the benefits of going to the cloud, what we're doing in the cloud, but what are we going to do next? What's the next thing that we're looking for? How can we improve what we're doing in the cloud? So that's what I'm here to talk to you about today. And this is actually my presentation, so hopefully this goes a little bit smoother. So the main thing we need to do is optimize. Yeah, the microphone's in the way, that's part of the problem. Yeah, it just shares, it's just, yeah. If I do this, is that better? No, I'm not gonna do that. So we need to optimize. We need to take our system and we need to make it better. And so the 4 things that we're looking at for optimization is we need to do it for cost, for performance, for ease of use, and also for our end users. So how are we gonna do that? Cost. At least 1/3 of our 100 petabytes of data has not been accessed over the last 2 years. So how can we optimize our storage to spend less money and still keep around that data? So one of the first things that we looked at that we're currently trying to implement is saving money on storage classes using S3 intelligent tiering. I talked about this a little bit in Ben's talk, but in S3 intelligent tiering, you throw your data in an S3 bucket and you say for a very not zero, but very small fee, hey, Amazon, tell me where this data should best go based off of its access patterns. And Amazon goes, okay, that sounds great. And they'll move it in between different classes like S3 standard, infrequent access, and the instant access glacial tier. This is something that we didn't have access to at a discount before. And so a lot of our tenants like DAX have been doing this manually. For most DAX, putting it in just S3 standard has been the go-to, but we have DAX like ASF, where I believe 98% of their data, petabytes of data, is in S3 infrequent access, and it does them a world of good. And so if we can let our tenants, our DAX, do that without having to do all of the legwork, it's a win for us. Also things like cloud optimized formats, where we can access data. You don't need to download an entire petabyte or terabyte file if you only need to look at a small portion of that on a map. And so putting things in cloud optimized formats, which allows users to download swaths of data, but only over the little chunk that they actually want to see, means less download for you, which means more savings for us. So Jess said she's not one of the cool NASA people, but we don't get to use fun pictures, and we're also required to break out every single acronym, which is why this page is really fun. I don't think anyone is going to be better off knowing that HTML stands for Hypertext Markup Language, but here we are. So, for compute, what are the things that we're doing to try to make this more optimized? So we use Amazon Web Services. We use the spot market for asynchronous batch compute. The spot market is an area where you can go to Amazon, and instead of just paying for dedicated compute, they will give you a discount for compute that's not currently being used. This has some volatility to it. You're not necessarily guaranteed that there's going to be enough spot market instances for what you're doing, depending on the load. A kind of funny use case for this is ASF, again, was one of the first users of the spot market, and they use it so frequently that they actually changed the cost of the spot market. They took such a big chunk of the available spot market at AWS that costs went up for everybody else, which is very interesting. So for Hype 3, they achieved a 70% savings from moving from EC2 on demand to using spot instances. Appears is also another application that had a combined reduced cost per request of over 94%, which they demoed at their Inspect and Adapt demo last year. And coming soon, we're hoping to put Harmony as well in the spot instances to include some savings. Another application, serverless. This is where we all get to just learn what HTML, JS, and API stand for. But what we're trying to get down to is instead of using just EC2 instances, if we're using a serverless application that is more static, if it's an application that works for your use case, it ends up being a lot cheaper. EC2 is kind of the standard that everyone kind of just jumps into, but there are options that if they work for you, can be a lot cheaper and give you a good savings. Finally, we have consolidation. So when we started out in the cloud, there were some decisions made that don't necessarily make sense now that we're a large enterprise cloud organization. So now that we have a firm foundation in cloud-based services, it's time to make sure that we are using a leaner approach to our systems. Infrastructure. So again, I just mentioned that a lot of people jump into EC2s, but Lambdas are a great way to have savings if it works for your use case. Things like picking the right database. There are different databases that are available as part of Amazon Web Services. Some are more expensive than others. Sometimes that cost is worth it. For our Cumulus organization, they use a database that is more expensive than alternatives, but it gives them the flexibility that allows their development work to move faster. But for other users, if that's not necessary, there are cheaper alternatives that you can switch to. And then moving data out of expensive stacks. One of our prime use cases is our metrics application, where we collect all of the data that we've been talking about and then provide it to our tenants for them to access. We currently use a paid-for Elasticsearch license that requires the data be in EBS volumes, which are very expensive. The amount of data that goes in and out of that system is constantly growing, and it is constantly getting more expensive. And so as part of one of our initiatives, we're moving to what we're calling the data lakehouse, where all of that data goes out of EBS and instead goes into S3 storage, which makes it significantly cheaper and also allows all of that data to be co-located so that we can combine things like access patterns, egress, storage with our cost data, which gives us more information and more insight as to how we can be better refined and more optimized in our spending. Let's talk about performance. So we're expecting that by the end of 2026, we will have 1.4 billion files on the cloud. I believe 200 petabytes worth of data is what we're looking at, if not more. It's a lot of data. So we need to get faster at ingesting that data. So how do we do that? So our Cumulus development team and our DAX, as Jess pointed out in that map, are continuing to improve their ingest performance, and that includes a couple of things. One of that is multi-part uploads for increased parallelization. More data coming in, we have to be more efficient in how that data is ingested into our system, or otherwise we're gonna start backing up. We have something called SIA, which is a service for ingest and archive, which will, I can't speak to SIA unfortunately in an intelligent manner because I'm afraid Patrick will chew me out. But it's going to be an application that will allow ingest to be more flexible and more optimized for our DAX. And then of course we have guidelines for enhancements for our common metadata repository, CMR, that allows data ingest to not be the bottleneck in our system. Data discovery. One of the things that we try to achieve with CMR is sub-second search for collection and granular discovery. This is a lofty goal, especially as more and more people are trying to access our data. And as our inventory grows, 1.4 billion files and counting, this is going to become more and more challenging. So things that we're looking to do for CMR that will allow our sub-second search to be more of a reality moving forward as our data grows. Includes auto-scaling and distributed caching, something that has been on the table for a very long time that we are very interested in moving forward through. Distributed caching would be phenomenal. And our goal is still that 99% of searches will be sub-second, and given how much data we have and how much access our data is being used, it's a lofty goal, one that we think and hope that we can achieve. Ease of use. So, first thing on the docket, relaxed registration. Right now, in order to access, you can search through our data without having to be a user, but to download data, you have to register with our system. We're hoping to change that so that there's not that burden of having to sign up for an account. So for non-ULID data, for ULID data with partners, we have a requirement that that data has to be behind a registration point. But for non-ULID data, we hope to remove the requirement of access and use something like the AWS STS, the Security Token Service credentials for access. If you've ever accessed our data through S3, currently you'll probably know that every hour you have to refresh your token. For an engineer, that's annoying. For someone that's not a software developer, it can be so burdensome that you turn away users. Open access is something that has really kind of made that a lot more accessible to many people. And open access is a wonderful tool, but at the same time, we shouldn't be forcing everyone to use open access if they don't want to. It's something that we should be doing at the point of exit. So we are hoping for no more 1 hour token expiration, and that we'll use something like AWS tokens, which people are largely familiar with, where possible. Requester pays. So right now, when we egress data, it's something that the government, the NASA currently pays for. Any data that goes out of our systems is something that we burden the cost. But the problem that we currently have is that that data has to stay within region where the data is, which is US West 2. So and certain organizations have their own clouds and infrastructure on AWS, but not in US West 2. So their ability to access that data outside of US West 2 would be great. But it's not something but that cost then significantly goes up for us. So requester pays means that a user, if they want to move data out of US West 2 into their own cloud, can do that if they're willing to pay for the cost. So for users bound to regions other than US West 2, we hope to allow S3 access for that data where they would simply pay for that model. In region will still, of course, be free, but out of region would be paid, but available, and it currently is not available. Cloud optimized formats for data. If we can reduce costs on our science data storage, we can examine the feasibility of storing copies of some of our data in cloud optimized formats. If you're not familiar with cloud optimized formats, some of our data products are quite large. And as I've alluded to earlier, you might not want to look at an entire globe worth of data if you're just focusing on science research in a small part of the country or a small region. A cloud optimized format would allow you to download a significant amount of data over a significant time period, but over that small area, meaning if you're looking at downloading things like sea surface temperature data, which can be huge chunks of data, but you only want that small part, you don't have to download so much data. And this has ramifications in a lot of areas. If we're adding this with requester pays and you're downloading it into a different instance, you're not having to download that entire file outside of US West 2, which means that it saves money on everyone, it saves money on egress, and it helps with the burden of having to have a system that can support terabytes, if not petabytes of data when you don't necessarily need it because your research is only looking at a small portion of the globe. Finally, and my favorite part is how can we optimize our systems for users? So data availability. I think we're all aware in this room that as NASA is a government agency, we don't have an unlimited budget. We can't just throw money at a problem and make it go away. We're not Facebook, we're not Amazon, we're not Google. We are working with a very strict budget that is kind of in flux depending on the circumstances or the year or political things that we should not get into. We are working on a finite amount of money. And so when we are working with a limited budget, we have to make sure that that budget is used as efficiently as possible. So by doing so, that means that we have better data availability and more data for the users that want to use it. For data access, we want to make sure that when you're accessing our data, if you're not ready to jump into things like direct S3 access, downloading small portions of data through things like cloud optimized formats. You are just used to downloading that directly from the DAC website. That data is still going to be available to you. We're not upending what we have previously done. We're just making sure that our systems are prepared for our early adopters who are starting to look to go into that cloud space. But the users who are still used to downloading data in the traditional method that they've been doing for years will still be able to access our data. And finally, barrier to entry. My background is in electrical engineering, specifically data engineering. And so as a data engineer, I'm very used to writing code and able to access data to make it optimized. But the majority of people downloading data aren't engineers, they're scientists. And for a scientist, getting into things like Jupyter Notebook can be burdensome, especially if they don't have a coding background. Now we're throwing things like cloud on top of that. It can be a limiting entry for users because it's an area where they're not an expert or maybe have no information whatsoever, and it can turn them away. So we need to make sure that our tooling is up to date and is more friendly for users so that they can access our data without having to have a degree in computer science, so that it's free and available for as many people as possible. That's all I've got, so. Questions? I was gonna say, if there's no questions about the actual talk I wrote, I'm gonna be kind of frustrated. Brian.
Yeah, do you or any, my name's Brian Daniel with Justice. Do you or anybody in the room know roughly how much of the data is non-ULID?
The question is, do we know how much of the data is non-ULID? Do you happen to know? I don't. Non-ULID.
I had that answer at my fingertips about 6 months ago.
I remember you.
But I don't have it right now. What I will say is there is more data that's under EULA than should be. The implementation of our EULA system made it easier for some DACs to apply EULA over everything back when we were only on premises. And that wasn't really a problem. You know, you just check, yeah, I'm okay. And then you would go and download your data. But with things like these 1 hour token expiration things, like having to verify a EULA on something that doesn't need a EULA becomes much more egregious. So it's in the like 40%, I think, but it should be lower than that.
I'm excited to hear your last point. I'm wondering if you can elaborate on it a bit, especially given the discussion before, the question at the beginning of this session, which is essentially will NASA provide compute? And if you start moving to providing tools and analysis to users who don't want to use code-based workflows, then you're gonna have to start offering at least some level of compute in order to provide the data. I'm just wondering if you can kind of provide some background on that.
Sure. So the question was regarding the last statement about what is the feasibility of providing more open-ended systems for users who don't have programming backgrounds? What is the feasibility of NASA providing compute? That's a difficult question to answer because Justin's raising his hand, so.
Very low. We're talking about a government system, talking about giving people who are outside of the security gates reading right access to government systems. When you frame it like that, it's a huge deal, right? And even if ESDIS wanted to do it, we cannot clear the security policies in the posture that's increasing, over time. We're always trying to find the best ways to down security with open access, open science. This will be an uphill battle for us to get that where you just open access to compute will be a very tough barrier for us to solve. The likelihood is low. Right? Just gonna be honest with you.
But we do have some indirect means of providing compute to the users. The services I mentioned in my talk, Appears or Hype, they're using government money to run those systems, and they're providing services to the users that would be very difficult for them to do on their own. So not open access, but to compute, but there is some compute there.
Yeah, and just to piggyback on what Doug said, there are some gray areas, right? Like I said earlier, OpenStage, we have a talk later on this afternoon. The way we're kind of skirting around that issue is we're using AWS credits to provide compute, to external users. And then there's other places like these SNC, Science Mission Computing System, environment, sorry. They have a lower security threshold for external users than something like the Earthdata cloud. We're still trying to figure it out, but there are other places that are, finding their own way to figure it out.
So to kind of close out that thought, there's also, I want to break this into two things. I have 3 minutes? Oh, wow. So compute is difficult because it's kind of like writing a blank check. There's a lot of security implications, as Justin mentioned, that make it difficult. But as far as removing barriers to entry, that is something that we can do and have some steps forward that have taken place. We have a cloud primer that's available online that kind of walks individuals through how they can start to put their information and their systems on the cloud so that they can quit running them on their own systems. It's something that we could probably update. I think that was something that came out of our UN TIM last year. But the dream would be to have a push button system where you would just click a button and everything would work. That is an incredibly lofty goal for the kind of analysis that we're talking about. I'm going to throw Amazon under the bus here a little bit because if you guys remember the dash buttons where it was a button that they'd ship you and you would just stick it under your sink and you'd push it and they'd send you paper towels and that was it. It didn't work. And they actually just sunsetted that about a week ago. And so if doing that for ordering paper towels is difficult, doing that for scientific analysis on data will be even worse. But there are steps that we're taking moving forward to try and remove slowly, step by step, those barriers to entry so that people who don't have software development backgrounds can still do analysis without having to be a professional programmer.
Yeah, and I'm thinking of the Hype and the Appears approach and maybe just plug and play like climatology, anomalies, subsetting, and I know subsettings are available through Omni for some data sets, but those are the kind of things that someone like my model or my director could do through a web interface.
we're at time, unless it's quick, Neil. Go, Neil.
Yeah, we do have to understand the class of users that needs help. Some people need more help than others. But for those who can and are willing to get their own cloud environment, one of the pieces of help that we might look into in the future, not a plan of record, is shipping them scripts through AWS that would help them set up their environment, and I think that would go a long way.
All right, we are at time now. All right, so, all right.
One last one?
Yeah, very
What
quick.
do we say? One last one.
The question might be
Actually,
quick.
one is you can do that. You don't need to write code and download data. And I think you mentioned that Giovanni in the cloud. Could you give us some update?
We mentioned what, sorry?
Giovanni in the cloud.
Giovanni in the cloud.
Not my area of expertise.
No, I think the first talk.
I mentioned what technologies they were using, but I couldn't give you an in-depth description about the current state of it. All right, we are done. Thanks to Nick, thanks to Jess, thanks to Jonathan and Ben in absentia. What's the one thing you're supposed to remember about this talk? We went to the cloud for equitable access to high-performance computing adjacent to the data. Thank you very much.
Joy Division and Marvin Gaye.